In this video, we will discuss different types of operations on our different vectors. And the first one that we're talking about is multiplying by a scalar. And notice that that tells you that a scalar is a real number, k, and the change will be in the magnitude of the vector. And so if k is negative, notice that you will end up with the opposite. Now, if you want to add vectors, you're really just adding those corresponding parts to each vector, and the resultant there, notice that we have that drawn in for us. So we will be doing what's called tip to tail, a way of drawing in our resultant. And in other words, for the resultant vector, we'll start with our initial and we'll end with that final terminal point up there. And then if we're subtracting, remember we are really just adding the difference. And again, we'll still be using tip to tail to put those vectors together. Now for vector addition, scalar multiplication, and subtraction, it is very straightforward in the process that you go through. If you had vectors v, and notice that v is given to us as a sub 1, b sub 1, then if I wanted to say k times v, then that's just going to be the product of k times a sub 1 and then k times b sub 1. And that's just your scalar multiplication. With your vector addition, then you would add your corresponding values, so a1 plus a sub 2, and then comma b sub 1 plus b sub 2. And then subtracting, then you would still say a sub 1 minus a sub 2, and then b sub 1 minus b sub 2. So going through some of the examples that we have here, notice for the first part they want us to multiply 2 times vector c. So in order to do that, then we're going to have our vector and we're going to say 2 times negative 4, comma 2 times 5. And so that resultant would be negative 8 and positive 10. Now looking at number 2, we need to add vectors a and b. And so if we add vectors a and b, we're going to have negative 6 plus 1, and then 2 plus 7. And so that's going to give us negative 5 and 9. The next one's c minus b, so vector c minus vector b. So we're going to have negative 4 minus 1. And then we're going to have 5 minus 7. And so our result here is going to be negative 5 and negative 2. And then for number 4, same process that you would think here. You've got vector a minus 3 times vector c. So that resultant vector a, we're going to have negative 6 minus 3 times c, which is going to be negative 4, and then we're going to have 2 minus 3 times 5. And so our resultant here should be 6, and then we're going to have negative 13. So for number 5, we have 1/2 times vector a minus b. So we're going to have 1/2 times, and vector a, we're going to have negative 6, then minus 1. And then we're going to have 1/2 times 2 minus 7. And so that resultant is going to be negative 4, comma, negative 6. And then number 6, we're going to have 4 times 1 plus 5 times negative 6, comma, and then 4 times 7 plus 5 times 2. And so that resultant there is going to be negative 26, comma 38. Okay, earlier we talked about a zero vector, which was a vector with a magnitude of 0. Now we're going to talk about a unit vector, and a unit vector is a vector with a magnitude of 1. So we can have any non-zero vector v, a unit vector u in the same direction of v can be written using the following rule. So our notation, again, unit vector u is going to be equal to 1 over the magnitude of vector v times vector v itself. So we're going to follow that pattern, and we're going to come up with our unit vectors. So looking at number 7 and number 8, they want us to find our unit vector. So the first thing we would need to do is find the magnitude of our vector v. And so that magnitude for this problem, we're going to have the square root of 25 plus 144. And so that's going to be the square root of 169, which is going to give us 13. So we found that. So now we're ready to write that unit vector. The unit vector, again, is 1 over the magnitude times the actual vector itself. And so once we do that scalar multiplication there, we're going to have negative 5 over 13, comma 12 over 13. And that's going to be our unit vector. All right, so let's try number 8. Same process again. We need to first find the magnitude of vector n. And so that's going to be the square root of 81 plus 144. And so working that out, that's going to give us the square root of 225, and that's going to give us 15. So now our vector, our unit vector, is going to be 1 over that magnitude times, again, the vector itself. And so that's going to give me 9 over 15, which you're welcome to reduce if you want to, and then comma 12 over 15. Okay, using that same set again, the first thing we need to do is find the magnitude of vector p. And so that's going to be the square root of 16 plus 1. So we're going to get the square root of 17. And so now we're ready for our unit vector. 1 over the square root of 17 times negative 4, comma negative 1. And we will need to rationalize here. We have negative 4 over root 17, and then negative 1 over root 17. And then if we rationalize that, then we're going to have our unit vector to be negative 4 root 17 over 17 and negative 1 root 17 over 17. All right, so looking at number 10, again, we're going to go through that same process. The first thing we need to do is find the magnitude of vector k, and that's going to be the square root of 16 squared plus negative 8 all squared. So it's going to give you the square root of 320. And you probably want to break this one down since we're having to do some rationalizing. So that's going to be 8 times the square root of 15. And so now for our unit vector, we're going to have 1 over 8 times the square root of 15 times the actual vector itself. And you'll probably want to do some simplifying here also. That is 16 over 8 root 15. And then negative 8 over 8 root 15. And those 8s, let's see, that 8's going to cancel, leaving a 2, and this was going to cancel, leaving a 1. And then when you rationalize this, you're going to have 2 times the square root of 15 over 15, and then you're going to have negative root 15 over 15. But do rationalize and simplify there. It's just going to make your answers a lot smaller. All right, so for number 11, notice they did not give us our vector in component form. So I would think we need to go through, and we can find this in component form if you want to, or go straight to your distance formula. I like going back over and finding my component form first, -1 minus the -7, and then go through. Since we have now our component form, then we can very quickly see that the magnitude of vector AB, I guess I'm going to discriminate against that A there, that's going to be the square root of 36 plus 36, and so that's going to give us let's see, the square root, so that's going to be 6 root 2. And then we're going to find our unit vector. So we're going to have 1 over 6 root 2 times the vector, and we're going to have 6, 6. Now, some of this I would expect us to be able to go ahead and do in our heads if you wanted to. And if we do that, of course, the 6's would cancel there, and you've got 1 over root 2, which is root 2 over 2. Again, 6's would cancel, and you've got your root 2 over 2 again. All right, and so for number 12, again, I would go through and rewrite vector PQ in its component form just to make it a little easier. So that's going to be 9, and -2 minus 4 is -6. And so now I can find the magnitude of vector Q. That's going to be the square root of 81 plus 36. And so that's going to break down to be the square root of 117, and that will reduce down to be 9 times 13, so 3 root 13. Now we're going to find our unit vector. So our unit vector, 1 over 3 root 13 times 9 comma -6. And so here we would cancel the 3 there, having a 3 left. So that's going to be 3 root 13 over 13. And then here cancel that 3, and that's 6. So we're going to have -2 root 13 all over 13. All right, now we're going to look at the standard unit vectors I and j as they're positioned along the x and y axis. So vector I is going to be in terms of, and we're going to look at our component form of 1, 0, and vector j is going to be 0, 1. Okay, now any vector v, and it's written in component form there, we really can change that up and rewrite it in terms of a linear combination, and we're going to have it written as a times I plus b times j. This is called your linear combination, and so what we're going to do is walk through the steps on how to show that that component form does become ai plus b times j. So we're going to rewrite the a and the I, or the I and j, as the original vectors. So it's going to be vector v is going to be a comma 0, and then plus b comma 0. Oh, nope, sorry, 0 comma b. Got those swapped. Okay, and notice it tells us that the next step is we're going to factor a and b out. So in other words, I'm going to rewrite this so that that is a times the vector 1, 0, plus, and then over here if I take out that b, that's going to be 0 comma 1. And so notice that again we're back to what we just looked at. So this is really going to be vector a times I plus b times j. And that, again, is your linear combination of vectors. So, writing in our linear combination form, notice what we're going to do with number 1. That's really saying here, when we go separate that out, we can rewrite that to be vector v is 2 times I plus 5 times j. It's the same idea there. And then for our next one in linear combination, vector n can be written as, negative 7I plus 3j. Now for number 3, notice we are not in component form yet. So the first thing we need to do is rewrite vector rs to our component form. And that's going to be negative 5 minus a negative 9. And then negative 6 minus 8, so negative 14. And now we can go write that in our component form for j, or for I, goodness, minus 14 times j. And then looking at our other problem, we're going to do the same thing. Again, we need to rewrite PQ in its component form. And that's going to be negative 2 minus a negative 10 and 5 minus 6. And so now we can rewrite this in component form to be 8 times I minus 1 times j. Okay, now for our trigonometric forms of that unit vector, and that's looks awful lot like the unit circle, and that's really what we're going back to. If u is a unit vector, then the terminal point of u lies on what's called the unit circle. And therefore, vector u in component form a comma b can really be written as, and this is taking us back to that unit circle. So in component form, instead of a comma b, we're going to rewrite this to be cosine of theta, comma, sine of theta. Or in a linear combination, we would say that u is equal to cosine theta of I plus sine theta j. And again, that's going to get us in our linear combination. And so looking on even a little further in the forms, because every vector v is the product of its magnitude and corresponding unit vector, then we're able to rewrite this in a couple of forms. Well, notice that we're going to take that magnitude of v, and we're going to write that times our unit vector u of cosine theta, comma, sine theta. And then we can go ahead and do that multiplication. So we can look at this as the magnitude of v times cosine theta, comma, magnitude of v times sine theta. And then we can also write this as a linear combination of the magnitude of vector v times cosine theta, and that's going to be the linear combination. You've got I plus magnitude of vector v sine theta, and then your linear combination j. Okay, for our next set, we need to find the component forms of each vector with the given magnitude and direction angle. So notice that we're going backwards now. Instead of looking at our magnitude and direction angle, trying to find those, that's what we're given, and we're going back to find your actual component form. So that means that I know for vector v, that component form, we're going to have 8 times cosine of 60, and I'm just plugging into the formula we just made earlier, 8 times sine of 60. And so here vector v is going to be 8 times cosine of 60 is going to be 1/2. 8 times sine of 60 is going to be root 3 over 2. And so here that component form for vector v is going to be 4 comma 4 root 3. All right, so looking at our next problem, number 6. Here again, we're going to go try to find our component form. So our component form for vector W, we're going to have 20 times cosine of 225, comma 20 times sine of 225. And so we're going to have 20 times cosine of 225. That's going to be a negative root 2 over 2, comma, and then 20 times, again, that 225 is in the third quadrant, so that's negative root 2 over 2. And so simplifying this, you're going to get negative 10 root 2, comma, negative 10 root 2. All right, and so moving on, looking at a couple of other problems here, same process. So to find our component form for vector K, you're going to have 12 times cosine of 150, and then you're going to have 12 times sine of 150. So K equals, and that's going to be 12 times, and cosine of 150, that's going to be negative root 3 over 2, and then, oops, need a comma, and then sine of 150 is going to be positive 1/2. And so our component form here for vector K is negative 6 root 3 and 6. All right, and finally looking at number 8. Now this one is not going to be one of those exact forms. So when we write it out, we are going to have a decimal answer. So for this one, we're going to have 30 times cosine of 340, and then 30 times sine of 340. And so after you put that in your calculators, you're going to end up with 28.19 and negative 10.26. Okay, for these, now we're going to go from our component form to our trigonometric form. So here's just another way of writing these vectors. So our trigonometric form, again, that's what we were just come up with earlier. So we definitely need to find our magnitude of vector V. And so that's going to be the square root of 15 squared plus 8 squared. So that's going to give me 17. And so now when we're going to go through, we've got to also find our direction angle, which looks like we're in the first quadrant. And so we're going to have tangent theta equals opposite over adjacent. And so theta here is going to give us 28.07 degrees. And so now we're ready to write out our vector. We're ready to see vector V in our component form. Here we're going to have 17 times cosine of 28.07, comma 17 sine of 28.07. You could also write this with that 17 factored out. So vector V is 17 times cosine of 28.07 and then sine of 28.07. Either one you want to write it is fine. All right, number 10. So number 10, again, we're going to go through, and first thing we need to do is find that magnitude. And so the magnitude of vector M is going to be the square root of negative 3 root 2 all squared plus negative root 6 all squared. So be careful and watch your signs there. So that's going to give me the square root of 24, which is going to be 2 root 6. And then we're going to have our tangent of theta equals opposite over adjacent. And so let's see, that's going to end up being theta if you put that in your calculators. And we've got to look, we're going to be back over in the third quadrant here. So do keep that in mind. When we go through and find this, we would go back and down. So you're going to be over here, and so that theta that you find, you're going to have to go through and add 180 to what you find, and hopefully you get an angle of 210 degrees. And when you do that, now you've got your direction angle, you've got your magnitude. So now you're ready to write your vector M is going to be 2 root 6 cosine of 210, and then 2 root 6 sine of 210. All right, so now let's look at a number 11. They've given us this in our linear combination, but remember that really this is saying that we have the values of -1 and 7. That's what it was in its component form. And so the magnitude of vector P is going to be the square root of 1 plus 49. And so that's going to give me 5 root 2. All right, and now to find our direction angle. Notice it looks like you're going to be in quadrant 2. And so if you go back here to quadrant 2, then your theta's here. And so we would have to subtract what we find from 180. And so hopefully you find that theta is going to be 98.13 degrees. And so now you're ready to write out your vector P is going to be 5 root 2 times cosine of 98.13, and then 5 root 2 sine of 98.13. All right, and the same thing for number 12. We're going to go ahead and I would look at that over to the side in its component form, which is going to be -2, 2. And then whenever you go through and find your magnitude of R, you're going to end up with the square root of 4 plus 4. So you're going to get 2 root 4, or 2 root 2, sorry. And then you're going to go through and find your theta. And again, keep in mind that this would be back here in this quadrant. And so what you find, you're going to have to subtract from 180. And so your theta here is going to end up being 135. And so your vector R is going to be 2 root 2 cosine 135, and then 2 root 2 sine 135. All right, last two problems, and goodness, there's a lot of writing we're going to have to do with these problems. The first thing we need to do is get our component form of vector AB. So that component form here is going to be -9 minus a -1, and you're going to have 3 minus 7. So there's our component form. And now we need the magnitude of vector AB. So that magnitude is going to be the square root of 64 plus 16. And so that's going to give me the square root of 80, which is going to be 4 root 5. Okay, and then we're going to have to go through and find our angle. We are going to be in the third quadrant. So whatever we find down here, you're going to have to add to 180. And so theta should be 206.56 degrees. And so now you're ready to go through and write all of this. So AB is going to be equal to 4 root 5 cosine 206.56, and then 4 root 5 cosine, or sine, sorry, of 206.56 degrees. All right, so now same process with number 14. The first thing you're going to want to do is find your component form for vector yz. And so that looks like it's going to be 2 comma -6. Then you're going to want your magnitude for yz. And that magnitude is going to be the square root of 4 plus 36. So that's going to give us 2 root 10. And then our angle, it looks like you're going to be over here in the 4th quadrant. And so you're going to have to subtract from 360. And so your theta, your direction angle, is going to be 288.43 degrees. And so now you're ready to write your vector yz. Is going to be 2 root 10 cosine 288.43 degrees, comma, 2 root 10 sine of 288.43 degrees.